Hi. So first, thank you so much for attending my talk today. My name is Flavio Brasil. I work at Twitter on the VM team. So we basically maintain a fork of the JVM. And today I'm going to be talking about Scala and Graal, but more focused on the performance aspect. So we have a hashtag. If you want to follow our work, you can follow this hashtag. And if you want to tweet something about the talk, please feel free to use the hashtag as well. The talk today has three main parts. So the first one is about, it's an introduction to Graal and why we adopted Graal. And the second part is about the profiling sessions that we've done and the kind of performance challenges that we see for Scala code bases. And the third part is about new optimizations that we've been working on to address some of these performance challenges. Cool. So we are going to start talking about Graal itself. First, what is Graal? Maybe some people don't know. And I'm going to start by telling you what Graal, the Graal that I'm going to talk today is not. So the Graal that I'm going to talk today is not the Graal VM. So the Graal VM is a very ambitious project by Oracle Labs. That is this idea of having a single VM that is able to run multiple languages, and then you can run this, embed this VM in different environments, like a database or JavaScript runtime, and etc. So it's a very ambitious project. We do not use Graal VM at Twitter. We just use Graal, that is a separate project, and it's like the basis of the Graal VM. The Graal project came from this interesting project called Maxine. So Maxine was a project that had a very interesting idea of rewriting the JVM in Java itself. So a VM that runs Java that is implemented in Java itself. So that's pretty cool. I'm not sure if this project is still active. It's also by Oracle Labs. But one piece of this project became what we call Graal today. That is the just-in-time compiler, okay? And that's what we use at Twitter. We use Graal as a just-in-time compiler. So maybe some people don't know what just-in-time compiler is. When you are running things on the JVM, you have some source code in a language, in a JVM language, like Scala or Java, Clojure, whatever. And then you have the language compiler that transforms the source code into bytecode. The initial versions of the JVM had an interpreter of this intermediate language. So the interpreter would basically look at instruction 0. Okay, I have to load something into a register. And then I have a multiplication. I have to load 2 registers and do a multiplication. So basically, it was like interpreting instruction by instruction. But interpreters are really hard to optimize. And then someone had this idea of, I think 20 years ago, of having a just-in-time compiler, a compiler that runs at runtime and transforms this bytecode into native code. So that's what Graal does. It's a just-in-time compiler that gets bytecode and transforms into optimized native code. And it's very advanced, and today we are going to see more or less how it works and how powerful just-in-time compilers are. I'm not going to talk about how we adopted Graal and the kind of challenges we had to adopt Graal. If you want to know more about that, please, this is a very good talk about the adoption by my colleague, Chris Tallinger. And yeah, I really recommend watching this talk as well. But the gist of the reasons is basically 2 main reasons. So the first one is having better performance. So at Twitter, we are operating at a very high scale, right? So just like small changes, like 5%, 3%, can be significant for us in terms of savings of the size of our clusters, right? And the second reason is that Graal is much easier to change than the default just-in-time compiler. And I'm going to explain more why. Cool. So just enabling Graal already gave us a very good savings. This is like the green line there is the Graal version running with Graal. And if you see the ratio, it's just enabling Graal gave us 11% improvement. So that's pretty significant for us given the scale that we are operating. And Graal is much easier to change because the default just-in-time compiler for the JVM is called C2. and it's a 20-year-old code base in C++. So you can imagine how inflexible, like over 20 years, code base that has like unsafe pointers and etc. can become. So C2 is really, really hard to change. And if we were still using C2, it would be very difficult for us to implement new optimizations. And Graal, being a new project in Java, more modern code base, it's much, much easier to change and understand. And you're going to see today like the kind of optimizations that we are doing. Cool, so that's an introduction about Graal and what we are using at Twitter. Now I'm going to talk about the performance challenges that we see when we are profiling applications running with the Graal just-time compiler. And Twitter is basically a Scala shop. We have mostly Scala services. So we are going to talk about the performance challenges that we see when we are profiling these services. I'm going to start with this. Scala is not Java. Even though Scala runs on the JVM, generates bytecode, Scala code bases have very different needs when it comes to performance. The JVM was optimized for 20 years or more for regular imperative code, but it has lots of trouble to execute functional Scala code in an efficient way. And it's interesting because Java is kind of becoming Scala. Over the time, you see more people using more functional abstractions and APIs that are composable, like completable future or reactive APIs as well. So slowly, Java is going to have the same kind of challenges as we see with our Scala applications. This is a profiling session using Intel vTune. So that's pretty interesting because this is the tweet service, and the methods that use CPU the most are not related to tweets. So most of the CPU usage goes into executing the infrastructure around the user code. So the first item there, the itable stub we are going to talk today, is the dispatching of interface calls. The second item is execution of futures. Promise is a type of future, and you have some natty stuff as well. So there's a lot of overhead around the user code. And the main reason for this overhead is actually the composable APIs that Scala applications normally use. And they are really a performance nightmare. They are really hard to optimize. And because they behave as interpreted languages. That idea of like just having a bytecode and interpreter that the JVM had in the past, that doesn't have much good performance, is what happens when you use these kind of composable APIs today with the JVM. I'm going to show you an example on how these composable APIs work. This is going to be just the beginning of an I/O implementation. So this is an I/O that produces a value of type T, and I'm going to implement the map method. So the map method receives a function that goes from T to U, and then it maps the result of the I/O to an I/O of U, okay? And the implementation, it's actually very, very simple. It just saves the initial I/O, that is this, and the transformation function, okay? If you see, it's just a case class. So it's just saving these two fields. And then I also created another version of I/O that is value, that allows you to lift a regular value T into an I/O of T. Okay, so very simple, and that's more or less how I/O implementations are done. Okay, and then you have, so when you are calling these methods, these I/O methods, you are creating this AST for execution, right? You are not actually executing anything. And then you have another step that is the interpretation and execution of this planning of this AST. So we are going to take a look on how this works. So let's say that we have, this is a very naive implementation, but it's more or less how these APIs are implemented. So you have the run method that receives an I/O, and then you do a pattern matching. If the I/O is a value, I can just extract the value, right? This is a very simple implementation without async support and etc., just as an example. And then if it's a map, I have to do two things. So the first one is run the initial I/O to get the value that needs to be mapped, and then call the transformation function to map the value from T to U that we saw before. Okay, so this is what's happening. We have like a creation of an AST of a plan, and then we have separate an execution and interpretation of this plan. And then I wrote this benchmark method. It's very dumb. It doesn't make much sense. And what it does, it just lifts a number into IO and does map +1, +1, +1 until you reach 10. So it doesn't make sense, but it simulates what happens with Scala, actual Scala applications that we have. That is, they are normally very large chains of transformations of this kind. So you have like the tweet service has, I don't know, thousands and thousands of transformations that it does just to serve you a tweet, for instance, and render the tweet. So it's basically simulating that. And then I wrote 2 benchmarks. This is using JMage, that is a benchmarking tool for the JVM. The first version of the benchmark is using, I called inlined. So what it does, it calls +10 to create this planning of execution, right? And then it calls run to do the actual interpretation and execution. And then I have a different version that is very similar. It calls +10 to create the planning, but it calls run not inlined to do the execution. And the run not inlined is actually just a method that calls run. And I separated it so I can use a JMage annotation that forces the method not to be inlined by the just-in-time compiler. Okay? So we have the difference between the benchmarks is just like the execution. The first one is probably going to be inlined with the planning, and the second one, the execution is separate from the planning of the I/O. But they have very different performance, right? So the inlined version has much better performance than the not inlined version. And how does a single indirection have this kind of effect, right? It doesn't make much sense. Let's try to understand that. When we look at the run method, we have some static information here, right? We know that it's going to do like the check for value or the check for map. So you have some static information that the just-in-time compiler can get from the compilation graph. And when you have the execution, this method, the context, the information of this method, separate from the caller, what happens, you have like 2 isolated pools of information. You can't join them, and when you can't join this information, you actually limit a lot the kind of optimizations that can be done. So let's look at inlining. Maybe people don't know how inlining works. So what the JVM, the just-in-time compiler does, it actually gets the body of the method and copies the body in the caller. Okay, so let's say that the JVM first inlines the +10 method. So what's going to happen? We have run, and then we have the implementation that we saw before, but n is basically the 20 that we passed to the method. Okay, so that's a process of inlining a method. And then I'm going to inline the run method, okay? And the run method, as we saw before, it's just a pattern matching of the I/O it receives. And then here, what happens, we have the information about the caller and the callee together, and that like makes the just-in-time compiler apply many optimizations. So for instance, it knows that the map method is always going to return a type of, an object that has type map. So it can actually not do the check if it's a value, for instance, for the initial I/O. One thing that's important as well, the transformation function is known at just-time compilation time. So it knows exactly which transformation function is going to be executed. But once the execution is separate from the planning, it doesn't know which transformation function is going to be executed. It just doesn't. It just knows that there are, I don't know, thousands of possible functions that are going to be executed, so it can't really optimize the execution. And that's a problem that we see, and that's why we have the itable stub call with a lot of CPU usage. And like I said, that's because these APIs behave as interpreted languages, and they are really hard to optimize. And it's even worse because they are embedded interpreted languages, so they are even more difficult to optimize. So if you have, for instance, like an I/O that has flat map, once you reach the flat map, you have to execute everything that comes before to know what's going to be executed next. So you can't apply partial evaluation, staging to optimize the execution, and the execution becomes highly dynamic and it's not really efficient. Okay, so this is the main problem, composable APIs. Now I'm going to talk about two optimizations that we worked on based on Graal to optimize composable APIs. So the first target is the future implementation. So we saw like CPU usage for the future in the profiling session. And it's a little different, the problem, but it's still because we are using composable APIs. And future is a strict API, so it has another challenge in terms of concurrency. So let's say that we have this future composition. I have a future f, and then I do map, doing +1, okay? What the future implementation needs to do, when map is called, it creates a new instance of a future, okay? And it's not going to wait for the result of the first future. It's not going to block or anything. It's just going to create a new future, and then register this new future with the previous future. So when the previous future finishes, it's going to let the new future know that the result is available. And that's not the actual implementation, but you can have an idea on how it works with this. So let's say that we have this implementation. The first step, as I said, is create a promise. That is a type of future, but it's a future that you can write its result. And then the next step is adding the new future to the queue, to the wait queue of the previous future. So the previous future knows which futures are waiting for the result. And here we are saving the transformation function f plus a promise to do the continuation. And then I just return the promise that is a type of future in the Twitter future implementation. So when the initial future finishes, the map implementation, it's going to flush the wait queue, and then it's going to see, okay, I have a map here. I'm going to apply the transformation function f, and then set the result. Okay? So now you know how a future more or less works under the hood. But there is a challenge. The future implementation has to assume that one future can have the map call, the map being called by concurrent threads. So you can have multiple threads adding new futures to the queue of the future. So you have to do synchronization. And that's something that's very expensive, because imagine every single call of a future transformation having to go through a synchronization point. So it doesn't have good performance. Cool, so I'm going to talk about the optimization that I did for this problem. But I'm going to use an isolated example so it's easier to follow, because the future implementation is very complex and it's hard to look at the compilation graph. So I have a task class that receives an initial value and then saves this value in a volatile, mutable value. Okay? And then I have two benchmarks. The first one is the unsafe version. It creates an instance of test, passing 0 as the initial value, and then uses the unsafe compare and swap API that the JVM provides. And it basically does a compare and swap. So you pass the t, that is the instance of the class, a pointer to the offset that the value is going to be, the expected value, and the new value that needs to be set. And this is something that's going to happen at the CPU level. It's a synchronization mechanism that happens at the CPU level. And then I have another version that has exactly the same behavior and actually exactly the same guarantees in terms of concurrency, but it uses a synchronized block. Okay? So create a new task class, synchronize on this task class, and then check if the value is the expected. So if it's 0, if it's not, return false. If it is, set the new value and return true. Okay, so very simple and the same behavior. But they have, at the time, Graal wasn't able to optimize both versions the same way. So the version using if-else and the synchronized block had much better performance than the unsafe version. And that's bad news, because the future implementation uses the compare and swap, the unsafe version, for adding futures to the queue of the previous future. Okay? So I started working on optimization for this problem. And then I saw that actually the if-else version can be optimized to just returning a Boolean true. So if you see C1 there, that's a constant Boolean. This is the completion graph that Graal produces. And the if-else version becomes just return a constant true, and that's why it has very good performance. But the version using the unsafe Graal at the time couldn't optimize that version the same way. So you had this crazy compilation graph that was much harder to execute and had much worse performance. Cool. So let's take a look why the if-else version can become just returning a constant true. And that shows like how just-time compilers are advanced and how they can do like really interesting things with our code. So this is not going to be the specific order that Graal uses, but I'm going to go through step by step explaining how it becomes just returning a constant true. So first it sees like, I just initialized the test class with 0, right? So it's never going to be different from 0, so Graal can actually remove the if-else condition, okay? And then it sees actually the T is never escaping the method. There's no way that another thread would have a reference to that instance. So actually the synchronization is not necessary at all. So it also gets rid of the synchronized block, okay? And then it sees actually T is never passed to another method. It never escapes the scope of this method. Okay, so the just-time compiler actually also removes the allocation and the assignment of the new value. And then you have just a constant true as the result. But like I said, at the time, Graal wasn't able to do the same kind of optimization because the compare and swap operation was opaque to the mechanism that does this optimization. And that's what I did. I actually extended the virtualization mechanism to also be able to see through these unsafe operations. So it's a pull request upstream. You can take a look at it if you like. And after the optimization, both versions of the if-else and unsafe, they both return a constant Boolean true, right? And then they have also the same performance, okay? So let's take a look why this helps us with the future implementation. As I said, the future implementation it uses the unsafe version of the compare and swap, right? So adding to the queue would make that opaque operation. So these two maps that happen there, they would have to actually be instantiated, but they are just transient futures. They are not escaping the methods. They can't be referenced by other threads. They actually don't need to be allocated at all. They are just transient. But before the optimization, because of the compare and swap that was the unsafe version, it would have to actually instantiate the future. And after the optimization, we can actually avoid allocating these transient futures. Okay. So the results were pretty good for this optimization. It was Q4 last year. So under regular load, so this is the tweets service running. We had 5% reduction in CPU usage. And then we also had 16% reduction in allocation rate. And that makes sense because we are not allocating those intermediate futures that we saw before. Just to clarify, this also includes code changes. The just-time compiler is very advanced, but it has limits. So I had to change the code to be more friendly to how the just-time compiler works. Okay? And then under stress, the result was even better. And that's what matters for us, because through this stress test, we determine the size of our cluster, how many instances of the service we need. And under stress, we had an improvement of 15% of what we call red line, that is like the limit where the service can still service requests without issues. Cool, so that's the first optimization. The second one is the itable stub calls. That is a more involved optimization, but I think I'm going to go step by step so everyone can follow how it works. So first, what is an itable stub? So the JVM has to for instance, if you are calling a method, and the method's not inlined, right? You have to actually call the method. The work that the JVM needs to do is actually find the memory position of that method. So it has to jump, first find where the method is, and then jump to that method position. And that's what the itable stub does. It's a C++ implementation that does this operation. Before explaining interface calls and itable stubs, I'm going to explain to you how virtual calls work. So virtual calls are regular class method calls. So let's say that we have a class memo that has the method speak, and then I have an implementation of memo that is a human. Okay? It has a new method speak that receives a language string, and then it overrides speak and overrides toString. The JVM creates static tables when it's loading these classes, so it's easy to do a virtual call, to dispatch a virtual call, and find the memory position of that method. So let's say that we have a memo that we are receiving this method test, and then I call the method speak. Okay? The JVM is going to use this information, these tables that were created during the loading of the classes that are called virtual tables. So the process of creating a virtual table happens this way. So first, you determine the virtual table of the superclass. So in the case of memo, the superclass is object, right? So let's say that we have two entries there. Object has more methods, but that's just for an example. So you have two entries, getClass and toString, and the number that you see there is a memory offset. So given a class and this offset, you can find the position of the memory of the method implementation. And then let's say that we are creating the table for the human class. The first step is looking at the superclass and copying the contents of the superclass virtual table. Okay, so it's going to add the getClass and toString from the superclass at the same offset. It doesn't change the offset that comes from the superclass. And then it adds a new method that is speak with offset 3, for instance. Okay? And then the same process happens with human. So it's going to copy the superclass vtable that is memo, and then it's going to have 3 entries from the superclass. And something interesting happens here. If you see the human class, it overrides the speak method from memo. Okay? But when it overrides, the JVM makes sure that the speak method is going to be at the same offset as the superclass. So regardless of the implementation of memo, the speak method is always going to have the offset 3. And then it adds the new method that is speak that receives string. So dispatching a virtual call, dispatching a method call that is a class method is very simple. Regardless of the implementation, the offset of the method is always going to be the same. Okay, so it's always going to be 3 in this case. Okay, so it's very simple and efficient. But the interface call is much more complicated because the JVM allows you to implement multiple interfaces, multiple traits. So you can't really have that fixed table approach that the virtual calls use. So you have to do something different. So let's say that we have human here that implements 2 interfaces. And then I have another, again, the method test. But I'm calling speak, and speak is actually an interface method now. It's not a class method. Okay? What the JVM does, many problems can be solved with an interaction, or most of the problems. So that's what the JVM does. It creates an interaction that is a table for interfaces. So let's say that we have this interaction table for human, and it has 1 entry for each interface that the class implements. Okay? And then each entry has an offset to something that is very similar to the virtual table that we saw before. Okay, so it works very similarly to what we saw for virtual calls. You just have this interface intermediate table where you have to search before. And to dispatch an interface call, what the JVM needs to do is first it uses a linear search on the interfaces. So it checks, for instance, like, is the first entry of the interaction table the one that I'm expecting that is memo? No, it's not. And then it goes to the next one. Is the next one memo? Cool, it is. And from there, I know which virtual table that I'm going to use, and it works very similarly to the virtual call that we saw before. But that's something very expensive, this linear search, and you also have additional memory jumps, and that's something also expensive. So imagine like APIs, like collection APIs, where one class can implement, I don't know, 10, 15 interfaces. So doing the linear search on this intermediate table can be really expensive, okay? So interface calls are much more expensive than virtual calls because of that. Cool, so then I started thinking, how can we optimize that, right? It seems to be like a essential problem, like to the problem itself on how to do the dispatching because of multiple inheritance of interfaces. And then I tried many things, I thought a lot about this, and I had this idea. So the JVM, before the just-in-time compiler compiles the bytecode to native code, it's always collecting profiling information on the types. So we have information from the profiling to know which implementations that we see for M here. So we know that M was like 70% of the time implementation A, 20% implementation B, and etc. So you have like exactly how many times you see each type and the probability of each type. And then I decided to go with a data-driven approach. So I changed Graal to dump this data. So for each invoke interface, which types we're seeing, which is like the superclass, how many methods it has, and then I imported this information into a relational database. So I could query and see, is there any patterns here that allow me to optimize the dispatching of invoke interface, okay? And then I saw something that was expected. The invoke interface call that happens the most is function1.apply, and that's because these composable APIs, they receive a function1 that is like receive one parameter and return the value, and they use function1 for that. That's what Scala uses when you have a lambda that is anonymous and has a single input that is using function1.apply. And that's expected because, as we saw before, as the execution normally is not in line with the definition of the computation, you don't really know which function is going to be called, and then you have to actually do an interface call using the itable stub. And then I saw something that was really promising. In many cases, all profiled implementations had the methods that was being dispatched at the same offset. And that's just coincidence. It's just the way the JVM works, and it's the way that Scala generates these function ones. So as you can see here, like function1.apply, in almost 1,500 cases, the offset is 672. Okay? So then I started thinking, maybe I can just jump to this offset and not do the linear search, like all these jumps, all these like mechanism with the itable stub that is very expensive. I also saw that like if you see the top invokes, like function1.apply is 1,500 invoke interfaces that we have for the tweet service, and almost 1,500 are at the same offset. So that would be a really cool optimization if I can just jump to this offset. But there's a complication. Let's say that I see, okay, I have all these profile types, and they have the same offset, so I'm going to jump to this offset. But if I have a call, I see two implementations, they have the same offset, but that's not a complete view of the classes that can be seen at this point of this call. So you can have like A and B during the profiling time, before the just-time compilation. They have the same offset. But what if I get a new implementation C? I have to check, does this implementation have the same method at the same offset or not? If it doesn't, I can't like continue doing the same kind of dispatching. And that was really challenging. The JVM, the just-time compilation in the JVM has a mechanism called de-optimization. So you can make an assumption, say, okay, I think here all implementations have the same offset. And then if the assumption is not true anymore, the JVM has a mechanism to say, this compilation is not valid anymore, recompile, reprofile, and recompile, right? But checking for the optimization was really challenging. I found a couple patterns, actually a few. Like if the class has a single method, I always know which method is going to be executed, but that wasn't really effective. I also saw that many classes have the same superclass, but checking the superclass was expensive because you have to jump to another place of the memory, and that was something expensive. And then I had this idea: what if I jump to the method, I go to that like 672 position and see, is this the method that I'm expecting or not, right? And then I used a fingerprint. The mechanism that uses the offset gives us a way of finding an implementation, an instance of a metadata class in the C++ code that is called method. So when you do like all these offset thing and etc., you reach an instance of a method call that is a metadata. And then you have a pointer there that actually points to the exact memory position where the native code is, okay? What I did is, instead of just reading this field, I added a new field that was exactly before this one. That is a fingerprint. And that allows me to check, is this the method that I'm expecting? It's a pair that considers the call, a hash, not a hash actually, it's a unique identifier given a pair of the method name plus signature. That way I can know, is this a method that I'm expecting or not? And that's something really, really effective, because I'm reading the fingerprint that is at a memory position very close to the field that I already have to read, that is the from compiled entry. So that way, when all implementations have the same offset, we can just do this really quick check and then read the position of the method. And that's something really effective, and the interface calls become almost as efficient as a regular virtual call, and that's a big difference in terms of performance. So this is the results. This is under stress, the tweet service. We were able to improve by 83% the number of requests per second that the service can handle. And then we have KPS, that is basically, because requests are batch, so services request like 200, 300 tweets from the tweet service. And under this other metric, we got 20% improvement. So we basically can reduce the cluster by 20%. There was also a significant drop in terms of latency. So this is the latency during the stress test. So it's first under regular loads, and then you start increasing the load until you reach the limits of the service. So before, it would reach 150, that was the limit, almost immediately. But after the optimization, the latency became like 100, always below 100 milliseconds. This is the profiling session using Intel vTune. Before, the table stub would use like 800 milliseconds during the profiling session, and after it's 340. It's a lot yet, and we are planning to do more optimizations, but it's a big difference in terms of how much the table stub is using in terms of CPU. So just to recap, we started using Graal for better performance. We got better performance at the beginning, and we are getting even much better performance now with new optimizations, because Graal is easy to change. So yeah, that's my talk. Thank you so much. Thank you. Do we have time for questions, or any questions? Go ahead.
Thanks for the talk, very interesting.
Thank you.
I have a question about the benchmark you showed where you were using unsafe versus synchronized. And I'm kind of wondering why this benchmark was useful, because usually you would have this thread contention and you probably would be rather interested in measuring how this holds up if you have 20 threads competing for this, right?
Yeah, makes sense. So there I wasn't really benchmarking concurrency. I was just benchmarking the cost of actually doing the method call. So as you can see there, because the previous, before the optimization, the compilation graph was much larger. So it would do many more things. And after the optimization, it does just like return a constant true. So that was my point with that benchmark, not about concurrency itself.
Okay, I mean, it triggered an improvement in Graal, so it can't be, so it wasn't useless, I suppose, but thanks.
Thank you. Cool. So yeah, I think that's it. Thank you so much.